of NMR imaging. I'm going to assume you a bit of a background in magnetic resonance phenomena, but really focus on imaging here. How do we take the MR phenomena? How do we create images? I'll start off with just sort of run-of-the-mill MRI, and then wrap up with some more what I call spectral-spatial concepts, so MR spectroscopic imaging. And if you want to either follow along now or later, I posted these slides up on my website. And I've actually posted a little bit more material than what I'll actually show today. So if you want to, if I go quickly through some of the equations or details, this is a good reference for you to come back to. So, just to get a little context here, the NMR phenomenon, as you may recall, was first discovered by Bloch and Purcell just after World War II. It took almost 30 years for the basically invention of what was then called NMR imaging to appear. So people to realize, well, this might be actually interesting biologically, and we can figure out some efficient tools to actually do in vivo imaging. Then about a decade later, in the early 80s, was when MRI systems became used clinically, and the name changed from nuclear magnetic resonance imaging to just MRI. And as you can see in the quote on the bottom, nuclear was associated with bombs and wars and God knows what. So who wanted to get in an MRI scanner if it was nuclear? And here's what, also to put the history of MR imaging in context, one of the first published human head MRIs. If you use your imagination, you can't imagine that is indeed a cross-section. Maybe you can tell it is an axial cross-section through somebody's brain. But the type of images, and this is even a little bit old, we can get today are much, much improved. And so this technology has come a long way over the past several decades. So here's what a typical MRI system is going to look like. And cut away on the other side here. Yes, I can use this. What you might see inside. And really what makes it an imaging system beyond just a spectrometer is that we go from having our radio frequency, magnet components. In this case, instead of having a sample, we have a subject. And what makes it an imaging system is these magnetic field gradient coils, or as we refer to them in imaging, the gradients. And looking a little closer at what those look like, is we got 3 sets of gradients. This enables us to do fully 3-dimensional, 2-dimensional, any orientation of imaging as we create these magnetic field gradients in X, Y, and Z directions like this. So on a basic level, how do we start to create images based on magnetic resonance phenomena? And what the magnetic field gradients do is that they're going to modulate the magnetic field as a function of position. So that's described in this equation here. And I'll just illustrate it in this picture here. So what the gradient is going to do, you can think of it as taking your main magnetic field, adding or subtracting a little bit of magnetic field on top of that. So you get some, we assume some linear relationship of the magnetic field versus position, which then, if we look at different positions in our subject, we're going to have precessions at different frequencies. And this is going to be what we're going to use to image to separate different positions. And we don't just do that in one direction. We can do that now in, say, our X or cross-sectional direction, as we typically refer to it, and we'll get the same type of phenomena here, right? So we can separate different positions based on applying these magnetic field gradients and look at the different precession rates or the resonance frequencies. And this principle, you can describe this in sort of your Bloch equations here. Won't go too much through the details here, but here's our final equation, or the key equation here is that the gradients, again, are modifying the Z component of our magnetic field, which therefore is changing our resonance frequency as a function of position. And how strong these gradients are and when we're applying them. So this simple example leads to what is called frequency encoding. And this is actually going to give us, in a typical MRI acquisition, this is going to give us one dimension of our image. So here's the nominal case. And you'll notice for the first half of this talk, I'm going to neglect other sources of frequency shift. I'll bring that back in later on when we talk about spectroscopic imaging and spectral-spatial principles. So this is, say we had 3 different objects here at different positions, but we have the same magnetic field at each location. Therefore, the signal we'd receive, is at the same frequency, no matter where we are in our subject. So if we do our sort of Fourier transform-based reconstruction, which is also what we use in imaging, then we're just going to get a lump of all of our subject here at the same position. And when we turn on our gradients, this is another way of looking at what I was showing before, but that our different positions now have different resonance frequencies in our signal. And the way that we're going to create a 1D image now is just simply a Fourier transform of the signal that we receive. And we're going to end up replacing these objects back in their original positions. So we got one dimension of image, but we want to get more. This is not going to give us those images we showed before. So here's our typical 2D MRI pulse sequence. And what I've described so far is a case where we turn on a magnetic field gradient, and we distinguish the different locations in our object based on their frequency as we acquire data during this period here. And the way that we add on other spatial dimensions to imaging is through what we call phase encoding, in this step here. And I'll also briefly go through the spatial selection through RF pulses as well. So briefly, the concept of phase encoding is, in this example, I'm going to add on this Y gradient in different steps. And we're going to do this between different TRs of our experiment and accumulate several measurements that are going to give us now information about our Y position. So say, in this example, the first TR, we do no gradient pulse applied on the Y-axis. Then in our next TR, we'd add some basically low frequency. So you have a slowly varying phase as a function of the Y position here that's been created by this small gradient pulse here. And as we increase the amplitude of this gradient pulse, we've allowed for more phase or more precession to occur across the Y dimension. So if we go back to the beginning here, we basically have no phase along this Y direction, little phase, more phase, and we're basically going to build up a set of these measurements to get now our encoding in our second and possibly third spatial dimensions, if we so desire. So this is the way you can look at this in terms of if you want to think about net magnetizations. The framework that turns out to be really useful for imaging is this concept that's known as K-space here. And K-space is a way that we're basically representing the cumulative effect of our gradients. So the important thing to know with gradient pulses or any sort of gradient field is that they're adding phase here onto our net magnetization. So this is our transverse magnetization component here. The gradients, as we apply them, add phase. And it's a cumulative effect. It's not an instantaneous effect. We always have to look back in time and say, well, how have we rotated our transverse magnetization vectors at all previous time within our TR here? So that's what this is representing at the top here. And by describing the effective gradients in K-space, this turns out to be very convenient, both in understanding how we do image acquisition, and I'll also use it to explain some concepts of RF excitation as well. So a little bit of math. You can go through these in the slides. What we end up here is basically a Fourier transform relationship now between our signal and, importantly, this is our signal now as a function of this K-space parameter, or the cumulative effect of all of our gradients And when you look at it in this way, you can say that the data that we're acquiring in an MRI experiment is acquired in this K-space, or this is the spatial frequency domain of our object. So it's the Fourier, this is little m here is our object as a function of space, and the Fourier transform of that is the domain that we're acquiring data. Similarly to an FID experiment, you're acquiring Fourier transform of your frequency content. In imaging, this is what the spatial frequency content, so K-space data, might typically look like. It's highly centered in low frequency information. But the high frequency information is important. So at this example is just to give you some intuition about what the K-space or spatial frequency represents in imaging, is that low frequency, this is a mask of just the low frequency K-space data, is representing a lot of the information, actually a lot of the signal, but it's only slowly varying features. So features that are very slowly varying in space are high spatial frequencies, are features like edges, and those are giving us the fine detail about the structure or giving us our spatial resolution. Another way you can look at the experiment here is that you look at different areas in K-space are encoding different patterns in space. That's what I've represented up here. So the center of K-space is encoding anything that's basically flat across our image. As you go further out in K-space, you might be encoding spatial patterns in our varying directions and with varying frequencies. And the premise of the imaging reconstruction is we take all these measurements at different K-space locations. They represent all these different spatial patterns in the image, and we combine them together based on the measurements to get our image. Okay, but back to the K-space formalism for how we acquire imaging data. So I'm going to pose the problem of imaging now as how do we sample all of this information in a two-dimensional or three-dimensional K-space, or then create a two-dimensional or three-dimensional image. So basically, we want to somehow sample all of this data, and then we're going to Fourier transform that to get back our image. So what K-space says here is that, again, where we are in K-space, or where we're basically acquiring data, is the net effect of our gradients. So the frequency encoding gradient here is doing something like this in K-space, and we refer to this as the K-space trajectories, is the path by which we are sampling data or which we're crossing K-space here. So the way we do 2D and 3D imaging typically is we might in 1TR, we're going to sample this region of K-space. Then when we add in phase encoding, if you look at that in the K-space perspective, we're now actually acquiring data in a different region of K-space. Or now we're getting this higher frequency spatial information about our object. And we're going to continue to do this across basically all of whatever region we want to cover in 2D, or I could add on a z gradient here. We can make this, in fact, a 3D K-space as well to get our image. Okay, so coming back to this perspective, what I've shown there is basically this part of the typical 2D MRI pulse sequence here, where every TR, we're stepping this phase encoding gradient, we're covering this 2D region in K-space, and then sometimes this is referred to as a 2D FT or 2D Fourier transform pulse sequence because we simply reconstruct this data with a 2D fast Fourier transform. Okay, so we'll link all the other thing I want to show here is that this is not actually the only way we can do imaging. So that is it turns out that's a very, the Cartesian or the 2DFT type pattern is the most robust and it's a very efficient way of doing it, but there are a number of other ways we can cover this, some sort of 2D region or even 3D region in K-space. Here I'm showing a handful of examples. We can do this in sort of an echo-planar type fashion. We try and cover it all within 1TR. Radial, these sort of combination of a radial and echoplanar or spirals, or if you can kind of dream it, you can almost do it. So very rich. Happy to talk more about the difference between these later on. And I'll leave that to you to check out if you want to see what the requirements of where we need to cover in K-space are. Because I want to move on to the other basic piece of the basic imaging experiment. And the other way we get localization is actually through the RF pulse. Okay, so if I start here with just an RF pulse, now no gradient. Every RF pulse is somehow selective in frequency. So the typical pulse we'll use in imaging is a sync type shape because there's an approximate Fourier transform relationship between the RF pulse shape here and the profile of the resulting transverse magnetization as a function of frequency here. Okay, so this is our pulse in absence of a gradient, and what are we going to do to image? Well, we need some sort of spatial encoding on this RF pulse. So what we're going to do is look about adding a gradient onto that RF pulse. And we can use this to somehow limit where we're actually exciting spins. In that 2D experiment, we want to only excite a slice of spins, and then within that slice, we'll use our frequency and phase encoding or one of these other trajectories to potentially create 2D images. Okay, so the one way you can look at this is say, okay, we've got our RF pulse on its own. The RF pulse has some frequency selectivity. Here we're choosing a sync pulse to get this basically rect type pulse profile and frequency. And with our gradient, now we've created this frequency versus position relationship. So that's going to map some profile and frequency to some profile in space. So what we're left with here is, instead of exciting a narrow range, exciting just a range in frequency, we're actually just exciting some sort of slice thickness or some sort of small region in space. So sort of putting that all together, this is the how we do spatially selective concepts with the RF excitation. Okay, so that's in 18 minutes. That was the basics of the MRI experiment on its own. And I know I'm jumping through some of this quickly. I've got some resources for you to go back to, check on anything at the end of this lecture and also in this syllabus. I encourage you to check out. But next I want to jump into the concepts of how we add spectroscopic information onto an imaging experiment. So to do that, I'm going to extend this concept of K-space into the spectroscopic or spectral domain. So one way you can define just a simple FID, pulse and acquire kind of experiment, or any sort of spectroscopic acquisition, as I'll call it, is that actually you can define it in this, what I like to call the KF space, which is simply time. But you can think of any sorts of off-resonance, whether it's chemical shift that we might be interested in, or other sources that change the main magnetic field, that these are equivalent to a constant gradient. This is a gradient that is always on. So therefore, we're always sort of, if we think of this in the K-space trajectory framework, we're always moving in this KF dimension. And just like our imaging experiment, right, where we acquire data in our spatial K-space, now we acquire data in our spectral, what I'll call spectral K-space to help put these things together. We do a Fourier transform, and we're back to our spectrum domain here. So with this framework in mind, you can think of, there's sort of the most basic spectroscopic imaging experiment. Here where I'm just showing this in sort of a 1D spatial case, but we could do this in more. Where we take this concept of phase encoding, we apply this before our data acquisition. And then what this looks like in now a spectral And spatial case space here is that our phase encoding is moving us in the spatial encoding direction, and then time is simply moving us in the spectral encoding dimension. And we can take now, for simplicity, I've only shown this in 2 dimensions, but we can extend this phase encoding in a through-board direction here or something and do multiple dimensions of imaging with this type of phase-encoded spectroscopic imaging strategy. But it doesn't stop there. Actually, we can take a lot of the tricks from imaging. We're thinking about, well, really what's the problem here? The problem is we just need to sample some 2 to now 4-dimensional region in case space. So we might have X, Y, Z in frequency. And we just need to figure out how to sample some region there, enough of a region such that we can reconstruct an image with whatever properties in terms of field of view and resolution we want. So one of the most common ways to accelerate a spectroscopic imaging strategy is what's called EPSI, or echoplanar spectroscopic imaging, where what we're doing here is playing an oscillating gradient in one direction. What that does is that moves up and down, just back and forth in our spatial encoding direction. And then now if we consider the spectral effects of the precession and due to different frequencies, that's going to just constantly move us along this spectral encoding direction here. So we're kind of creating this zigzag pattern in a spectral encoding dimension. Or if we look at that in one more way here, just turning it on its side, doesn't matter how we look at it, right? Is that you can think of it as having our imaging, sort of imaging gradient on here, which gives us, again, information about some spatial dimension, and then our frequency dimension that is always giving us accumulating information. So this sort of idea of off resonance being a constant gradient. There are some other subtleties here. This doesn't come for free. We do have some requirements in terms of our field of view and resolution that we want to achieve, both in spectral and spatial dimensions. These type of fast imaging strategies do require some trade-off of spatial resolution and spectral bandwidth. And again, as with imaging, when spectroscopic imaging, there's multiple ways in which we can acquire both our spectral and spatial information, depending on how we choose to manipulate the gradients. So this is an example of the echoplanar trajectory and how we might stack that up to get 2 spatial dimensions here and 1 spectral dimension. What we do between TRs is sort of stack up these zigzag patterns. Leave that up for a sec. Such that we cover what is a 3D region in K-space. It's 2 dimensions of spatial encoding, 1 dimension of frequency encoding or time. And that's not the only way we can do spectroscopic encoding as well. We can do things like spiral spectroscopic encoding. So again, the fundamental problem here is to cover this 3-dimensional K-space region here somehow. And again, if you can dream it up, there's within the limits of your gradient coils and amplifiers, you can do these things. Another thing here, you can do these sort of concentric rings. So there's, I think, some nice, I like to look at these. There's some nice symmetry in them, nice properties, but there's some disadvantages and advantages to these different approaches. All right. So that, in a nutshell, is how we add imaging to a spectroscopic experiment. And the remainder of time here, I'm going to look at the concept of spectral-spatial RF pulses. So analogously to our spectroscopic imaging acquisition, where we want to now both encode spectral and spatial information, this is going back to the RF pulse side, where we want to be considering both the spectral and spatial components of our RF excitation. And can actually look at this in some very similar ways to how we do spectroscopic imaging as well. So this would be a typical spectral-spatial pulse design, and these are designed both with their spatial component in consideration. So I'm going to show this type of picture a few times here, where we have position versus frequency. We want to maybe select for some specific slice in our object, as well as, and we want to have some sort of selectivity and frequency here as well. So in this example, the main excitation lobe is around, has some bandwidth around our center frequency and has some slice thickness of about 5 millimeters. And these typically use an echoplanar style gradient, just like I showed on the spectroscopic imaging acquisition side, and for the same reasons here, and then I'll illustrate that in just a sec. Okay, but to understand spectral-spatial pulses, we can actually take this. So I'm bombarding you with K-space this morning. You're going to, hopefully it's on your mind all day. We can actually put K-space into our excitation as well. And this turns out to be very helpful for understanding spectral-spatial RF pulses. This is, I'm pushing K-space on you. And this is kind of the everything all together. Spatial K-space, spectral K-space, and RF excitation on top of that. So it's a lot to put in there. If you need it might be helpful to look back at this if anything is tricky this time around. So first I want to, so the concept of excitation K-space is like this, is that we can think of our RF pulse as basically playing out some pattern in now K-space, and the effect on our magnetization is going to be approximately a Fourier transform of whatever pattern we're creating here in our excitation K-space. That the Fourier transform of that is going to be what we're going to get in our magnetization. So here's our typical slice-selective RF pulse, and kind of tried to illustrate a little bit here, but we're creating some excitation along this little zigzag pattern here in excitation K-space. So here I'm just flipping that on its side. So I'm saying we create some pattern due to our RF pulse in this now spectral and spatial K-space domain. And if we want to figure out what our RF pulse is doing in both our spectral and spatial domains, then we simply take, or approximately take, a Fourier transform, or we can do other tools to be more precise. But we approximately take a Fourier transform of this pattern, which is defined by our RF pulse and our gradient. So our gradient telling us where we're going, and our actual RF telling us what the pattern is here. We can take a Fourier transform, more or less, of this and derive, now, what is the spectral and spatial response of our RF pulse? And this was actually a very simple pulse. This is our slice-selective RF pulse, right? And we can actually, even from this very simple pulse, we can glean a couple things from this example. So here we have some slice thickness, and if I plot this as a function across position at a few different frequencies, we'll see that we select a slice, like I showed earlier in the talk here. But if we look at, now if we consider off-resonance frequency, so if we have some chemical shift-induced change in frequency, we actually get this effect, what we often refer to in imaging as the chemical shift slice misregistration effect, whereby just with our plain spatially selective RF pulse, we get the effect of having chemical shift is that the location of this slice actually moves in our object here. So now we can take this a step further, and that's where the spectral-spatial pulses come in. So this is what the profile looks again, just of our simple excitation pulse, or spatially selective excitation pulse. And now we can try to be more clever and say, well, let's consider both the spectral and spatial components of our RF pulse, but when we design this pulse. So your typical spectral-spatial pulse looks something like this, and it actually basically consists of two RF pulses. To some approximation, it consists of a spectral pulse, which is the overall envelope here, and then little spatial subpulses. And then we have this gradient here that creates this zigzag or echoplanar trajectory, but now and looks just the same as our fast spectroscopic imaging experiment. And we've got, again, our spatial dimension and our frequency dimension encoding. But what this, the way you want to look at this type of pulse is say, with this pattern here, what is the shape that we're imparting in excitation k-space by our RF pulse? And so if we just converted this waveform here to be shown in this spectral-spatial excitation k-space, then again we just have a Fourier transform relationship, or approximately, between this pattern and what our spectral and spatial profile is. So the difference between this pulse and the previous pulse, which is just our run-of-the-mill slice select, is we're actually trying now to consider, well, what's happening when we consider this spectral excitation dimension here. So if we've designed our spectral and our spatial pulses correctly, now we can get a profile that's selective in space and selective in frequency. You notice this is not perfect. We have these little sort of side bands here. So there is some trade-offs to this design. There are some tools to kind of reduce these, or and some limitations similar to fast spectroscopic imaging, but usually a worthwhile trade-off. And to take hopefully a little bit of the intimidation factor out of spectral spatial pulses, I just want to walk you through what basically happens and how I designed that pulse on the last slide. For a simple design, it's really not that complicated, not much more than your typical RF pulse design problem, where what I did was I designed a spectral pulse. So I said, well, I want to select out, in this case, I just want to excite some range and frequency defined by this. And that created that overall, this overall green envelope here. Then designed a spatially selective pulse and a corresponding gradient. So I said with that, well, I want to only excite a, say, 5 millimeter slice thickness. And then there's a formula here that to combine these two pulse designs together, and provided if you put in the right constraints into these two, you'll get something like this. There are repetitions here due to the sampling effects, but there's not much more that goes into spectral spatial pulse design. And here's sort of that illustrated in the RF and the gradient pulse. So you can consider your spectral pulse design as you're designing for this constant gradient due to chemical shift or other sources of off resonance. And that is a long pulse, like, say, in this case, 20 milliseconds. Then you design these short spatial, what I call spatial subpulses, which are just the slice selectives, or like our original slice selective RF pulse. And these have their own spectral and spatial profile that we're going to combine together to get in this pulse design that I showed before. And I'll show, it's my last slide here. I'll wrap up with this and show one a little bit more complex, but sort of practical example. This type of pulse is used for our human prostate cancer spectroscopic imaging studies, where you can go even a step further than that simple example I showed. So in this case, it's shown a little bit differently, but look up here. You can see, well, let's start off with the pulse here. So we have an oscillating echoplanar type gradient, same as I showed before. And then the RF pattern here has been designed with two considerations in mind. First is to, again, only excite a given region in space. And a little bit more subtlety was put into the spectral component of this pulse design. So it's not that you just have to excite one bandwidth and not outside of that. This was actually chosen to fully, in this case it's a refocusing pulse, so fully refocus some region where we had some metabolites of interest for prostate cancer, to actually not excite around the primary lipid resonances, and then to partially refocus water, in this case, water being often sort of a confounder in vivo spectroscopic imaging applications. So there's sort of, I wanted to show this as it's a step beyond of just exciting a region in the spectrum, a region in space. You can be more clever or creative with what you want to do in the spectrum, and you could also potentially do this in space as well. And with that, I will wrap up and leave it on this. And again, these links I put all in the syllabus for the program, as well as a link to these slides, and there's a few other points in there. Yeah, I'm happy to take any questions and discuss things over breakfast as well. So thank you very much.